four different structures. You have four different bromides, right? And what is important here to recognize is that the living group is the same, all of them. So in SN1, we look at the carbon attached to that. This is primary, secondary. This is also secondary, and the last one is tertiary. And which one is better? D is that. Because SN1 needs to form the carbocations that will be most stable for this one. Second question asks you about the SN2 mechanism, and the same exact four different substrates are given. In SN2, now which one is the best? A. Next question is which reaction takes place at the fastest rate? And the nucleophile is the same, solvent is the same, temperature is the same, right? The only thing that changed is the substrate. And again, you look at the nucleophile, recognizing that it's a sulfur-containing nucleophile, that they are particularly good nucleophile. So it is likely to undergo an SN2 process. So in SN2 now, we look at again the same thing, that the carbon you have, this is primary, and so is this one. This is primary, and so is this one. So all of them are primary carbon. The thing that changed is chloride versus bromide and the product. Now obviously, because SH is not a good base, you can rule out the elimination product. Okay. And of the two, which one works better? A or C? C, because bromine is a better leaving. Right? So C is that. Identify the mechanism most responsible for the major product of the following reaction. Okay. And again, you need to recognize what kind of reaction this would undergo. Okay, you're using a strong base, sodium oxide, and ethanol, and heat. And so this is a secondary carbon. And secondary carbon with an alkoxide, what reaction is most favorable? U1 into SN1, SN2? Elimination or substitution? So elimination would be preferred in this case, right? And if it was primary, then the substitution would be predominant. But in this case, elimination is preferable, and it is going to undergo an E2 process. What is the major product of the reaction below? And again, you recognize the cyanide, Cn minus, is a good nucleophile and a poor base. It's given a polar atomic solvent DMSO at room temperature. And you have two chiral centers in the substrate. But the relevant one is this one. So what we expect to see as inversion of configuration and that carbon, not the other one. So the cyanide will attack from this side and displace the bromine. So we are looking for cyanide on that side. This is one of them. But here, they also switch this one. That's not going to work. So B is the answer, where this is retained and this is inverted. Okay, I'm going to skip the next problem because we didn't discuss it yet. And go to the last one, 855. It's telling you that trimethyl tetrafluoroborate reacts with methanol to give dimethyl ether, which is CH2OC. Which equation, including the card arrows, best represents the reducibility state of the mechanism? So this is the compound that they are reacting with. And methanol is reacting with this. Okay, so the first one, when you examine that, one thing you immediately recognize that that is, therefore, if you cannot form, you cannot react. Right? Now the next two, okay, the main difference, this reaction will go fast. But the problem is that you are using methanol where you get the methoxide. Right? So you don't have much methoxide in the solvent. This is the one where the methanol attacks this and forms this cation, generating the dimethyl ether. That would be the